right. Let me close this. All right, so welcome to the channel, I guess, if that's what they're called. I tried to think about what I would be coding today. However, I wasn't really sure. So I'll talk a little bit about our project that I want to do, and we'll see where we can get. As usual, this is just me doing my standard coding on a Saturday. I don't plan my coding at all, and it's all unscripted, so to speak, so it is what it is. Today I'm obviously wearing very festive clothes. You can see my cool shirt. I think this will fit very well with the stream today. So, there's a project that I've wanted to do since I was probably maybe even in elementary school, which is build a little supercomputer. Now, obviously, there's probably no good way to build a supercomputer in the sense that I cannot build, without a lot of resources, a computer which is competitive with the top computers in the world. You could do this maybe 20 years ago, but now I don't think it's feasible. Nonetheless, I would like to build something that sort of resembles the architecture of a supercomputer. So you have different processors, so to speak, different parts of memory, different disks, basically a bunch of computers clustered together. Not necessarily in the, however you pronounce it, Beowulf, is that how you say it? The Beowulf cluster style, but something like that. And now that we have things like Raspberry Pis and, whatever it may be, we could, in principle, link all those together. And I think that's what I'm going to do for my project. Get a bunch of those little single board computers, network them together on a high-speed network, like a gigabit, link them all to a gigabit switch or something, and then, write some code that manages computations across them. So, this desire came from when I was a kid reading about the number pi, there were various world records held in computing pi. Just a second. Just want to make sure the stream has good fidelity. Anyway, so there are all these records of pi computations, which were all done on supercomputers. If you wanted to compute millions or billions of digits of pi, you do it on a supercomputer. And there were two sort of inspirational people that kind of took pi into their own hands. One was Bill Gosper, who computed the continued fraction expansion of pi to some millions of terms, I believe, which equated to, I don't remember how many digits it was, maybe hundreds of millions of digits, maybe it was a billion, I don't remember. He computed pi on his symbolic Lisp machine. The other person, which I've done, I've computed a pi in a single program before, so that's kind of off my bucket list. In fact, that was one of the first programs that I ever wrote. The next, influence, I would say, was the Chodnovsky brothers. They are two mathematicians, incredibly smart, who made the best formula, I would say, to compute pi. Not asymptotically best, but practical best. They did something that I thought was interesting as well. Not only did they make the formula, but they also built in their New York apartment a supercomputer cluster out of mail order parts. And because I think, as the story goes, they were fed up with the supercomputer in Minneapolis because of disconnect, it's time sliced, so on and so forth. if they had their own machine, they could compute it however they want, they could run it however long they want, and so on and so forth. So I've always wanted to copy that, basically. I've always wanted to build my own supercomputer in my own home and calculate pi on it, which is exactly what they did. And I think they computed around 1 billion digits. So yeah, that's one of the other things that I wanted to do. Fortunately, now I don't have to take an entire living room to build a supercomputer. I could probably fit a, supercomputer, quote unquote, in the shoebox with, whatever single board computer. So building the supercomputer cluster is one task, which is something that perhaps we can discuss another time. But for me personally, I'm not so much of a hardware guy. I have an interest in hardware, and there are interesting problems in building maybe a power supply to power all of these things. I mean, if you have 10 computers, ideally you don't want 10 cables running out of the box with 10 wall warts. Ideally you have one power rail or whatever it is, and you power them all. There are interesting problems there, but there's, in my opinion, or at least for my capabilities, the more difficult problem is the problem of distributed computation on these things. Now, there's a lot of tools out there to do distributed computation. It would be wise if I researched those and perhaps use them, like MPI and so on. However, as a start, I think it'd be fun to kind of architect my own, to kind of see what problems are involved in distributed numerical computation, I should say, and just learn more about it. And then maybe, if it's appropriate, to actually use something like MPI. Does a machine with 512 commodity cores and 132 gigabytes of memory count as a supercomputer? Yeah, in the sense that I'm talking about a supercomputer, I would say so. As long as it's a machine, I'm basically saying a supercomputer is a cluster of machines that work in unison to solve one problem. Obviously, the line between supercomputer and even desktop machine is blurred a little bit, because now we have, at work, for example, I have a machine with 24 logical cores and, a ton of memory, which was better than any supercomputer some years ago. And it is distributed. The only benefit is that it has shared memory. So the big differentiator here with a cluster of computers that are networked together is that we don't have the same sort of shared memory, unless there are ways of doing shared memory, but it's very tricky. So you have to have some sort of message passing interface and so on. So what I'd like to start programming, to kind of get to the point, is software that can, compute pi. To be more specific, actually, I'd like to build some software that can do distributed computation of hypergeometric series. I actually have a tablet here that I would like to use, for drawing on a pen, with a pen on the machine. However, I've noticed that it's actually more difficult to draw on a tablet than I first thought. My handwriting is really bad, so I actually need to practice with that before I actually start writing. So, hypergeometric series, I suppose I can just go to Wikipedia, if I can find it, and show a quick little thing. I'm not going to explain everything about them. But the point is that it's a series that kind of looks like this. I can zoom in maybe. So here's the series. Hypergeometric, this is one kind of series, I should say. This is called the 2f1 hypergeometric function. It takes 3 parameters, a, b, and c, and then this is kind of the variable of the function, I guess. So what you do is you have kind of the numerator parameters, which are the first however many separated by a semicolon. And those are the things that show up in the numerator of the sum. We have the denominator parameters. Here we just have c, and those show up in the denominator of the sum. And then our formal parameter z is the power parameter, the typical series parameter that you have, and we just divide that by n factorial, which is mostly a historical thing, because the factorial here could actually be a denominator parameter, but it's just convenient because this makes, for example, exponential series kind of the trivial 2f1 hypergeometric function. Because if this is just 1 right here, then we have the exponential function. So the general hypergeometric series, let's see if it's down here somewhere, is that, but with any number of numerator and denominator combinations. So, okay, this is all about the 2f1 generalized hypergeometric function is what I want. So here's the general form. These a's are the numerator parameters, these b's are the denominator. Since they're p numerator, we put the p here, and since they're q denominator, we put the q here. So a pfq hypergeometric function is something with p numerator parameters and q denominator parameters. The parameters need some special structure, which is each of these numbers is actually representative of something called the Pochhammer symbol. I don't actually know if that's how it's pronounced. I'm sure it's maybe Pochhammer or something like that. I don't know. But anyway, Pochhammer symbol is kind of like a factorial. You can see here that Pochhammer of 0 is just 1, kind of like 0 factorial is 1. Then Pochhammer a of n is a times a plus 1 times a plus 2, blah, blah, blah. So we have a total of n terms here. So trivially, if we had the Pochhammer symbol, just to write it here, if we had 1 sub n, then this is equal to 1 times 2 times ... times n minus 1, because that's a total of n parameters. And of course, this equals n minus 1 factorial. So it's very much like factorial, except slightly generalized. The reason why we use Pochhammer symbols here in the representation of the hypergeometric function is because it gives the function or series a very special property. A geometric series, if we remember what a geometric series is, it's a series where the ratio of subsequent terms is constant. So if the first term of a series is 1, and then the next one is a 2, and the next one's 4, 8, 16, well, 16 divided by 8 is 2, 8 divided by 4 is 2, it's 2 each time. Hypergeometric series is a generalization of that. What the generalization is subsequent ratios of terms is a rational function in the summing parameter. So we can actually see that here. So if we have a series beta 0 plus beta 1z plus beta 2z squared, and so on, we say that the function is hypergeometric if for any n, beta n plus 1 over beta n is some rational function, a of n over b of n, as long as it's a rational function in n. So since this is a rational function, then we can factorize the numerator and denominator. They'll both be polynomials. If we can factorize the numerator and denominator, then naturally we get this Pochhammer structure, meaning you can always decompose any hypergeometric function that satisfies this ratio property into one which is a product of Pochhammer symbols in the numerator and denominator. So kind of what's the point of these? I mean,